Okay, good day. I am Mr. McCully. This is dual enrollment pre-calculus, and this is lesson number 26, solving trigonometric equations. Let's get right to it. So we have some learning goals today. Today we're going to use standard algebra techniques to solve trigonometric equations. We're going to solve trigonometric equations of quadratic type. We're going to solve trigonometric equations involving multiple angles, and we're going to use inverse trig functions to solve trigonometric equations. As always, we have to keep in mind the unit circle. And let's get to some fairly simple stuff first. And these are kind of elementary examples, but trig functions are periodic, and therefore they have more than one solution. So if we talk about the sine of x equaling to 1/2, the solution is an intersection of a graph of a function, or actually maybe two functions. So if I go y equals, and let's clear this out and say sine x, and then we say 1/2. And so the sine x function you're used to, the half is just a horizontal line. And let's talk about our window here. So our window goes from negative pi over, or excuse me, negative 2 pi to positive 2 pi, and our scale is pi over 2, the y minimum negative 2, y max 2, and the scale is 1. So when I go to graph, ooh, that's wrong. Oh, I know what's wrong. We want to be in radian mode instead of degree mode. Sometimes that happens. Hit graph. Okay, so we know that the trig function is infinite. It's going to go on forever to the left and on to the right. And we see a half right here. And just in this window alone, we see 1, 2, 3, 4 solutions to the equation sine x equal to a half. And so there are multiple solutions just if along the graphs. We can also say that the solution has multiple values on the unit circle. So if I go back to the unit circle and we just talk about one revolution around the unit circle, remember that sine x or sine theta is equal to the y value. We see that there are two values where we have a y of a half. So just on 0 to 2 pi, not the infinite values, just that one turn around the circle, there are still two solutions. So when they say solve the equation, it's very likely that you're going to have more than one solution. Now, there are two different ways they're going to ask this question. They're going to ask this question, solve, and they're going to say find all solutions over 0 to 2 pi. Now, the find all the solutions over 0 to 2 pi is the easy one because we're just looking for the unit circle. And we've already said that there are two values that make that equal or make that true. And in this particular instance, this equation says what angle measure gives you a sine of a half. That's what this says. And so we get pi over 6. The sine of pi over 6 gives me a half, and the sine of 5 pi over 6 gives me a half. So my solution, so part A, solve over 0 to 2 pi, and this is including 0, and this is everything up to but not including 2 pi, just interval notation. And so our values for x that make that true, x equal to pi over 6 and 5 pi over 6. All right. So part B. Well, part B says find all the solutions or solve. So find all the solutions. Well, all of the solutions will be pi over 6 and 5 pi over 6. And I want to erase that comma. I'm not quite there. 5 pi over 6 and all multiples of full circles around, or in terms of the graph, this one, this one, this one, and this one. And then as we go further to the left and further to the right, all of the multiples of that. So we can't write an infinite number of answers. What we're going to do is we're going to come up with a way to express the original pi over 6 and 5 pi over 6 plus all of the multiples. So if I go, let's just talk about pi over 6 for a second. If I go pi over 6, so there's my first solution for pi over 6. If I go all the way around and then up to pi over 6, well, that next one will be, we'll do it here, pi over 6 plus 2 pi, which would be pi over 6 plus 12 pi over 6, because that's 2 pi, to get 13 pi over 6 is what that next one would be. So 13 pi over 6. And then the next one would be 2 pi more than that. And so we'd add another 12 pi over 6, which would give us 25 pi over 6, dot, dot, dot. And so the same thing could be true for 5 pi over 6. The first one could be 5 pi over 6, and then you could go all the way around, and so we're taking that 5 pi over 6 and adding multiples of 2 pi to that. So we want to do that in a general manner. And so what we're going to do is we're going to say it's pi over 6 plus 2 pi n, so 2 pi times some n value, comma, 5 pi over 6 plus 2 pi n, and then we're going to tack on where n is an integer. And remember, integers are the counting numbers plus the negative counting numbers. So, well, 1, 2, 3, 4, 5, and -1, -2, -3, -4, -5, and so on from that. So this says find pi over 6 plus any multiple of a full circle around from that point. And so those are the two types of questions they're basically going to ask in this problem. Now, come on, go to the next slide. There we go. Tools for solving. Substitution. Here's an example. Transforming an equation so that it only has one trig function usually makes it easier to solve. So if you end up with something like cosine squared plus sine plus one of the others, try and do a simple transformation or a substitution to get all of the trig functions to be the same sign. So it's like sine, all cosine, all tangent. Simplifying example, if you have a equation with one term or a fraction, is much easier to solve than an equation with two. So if you can simplify a sum of fractions into a single fraction, that's a good way to do it. Multiple angles, and we've done one of these in a previous lesson, but I think I have an example of that here, where you solve the equation if it were just x and then find the multiple angles. And so when I talk about a multiple angle, I'll say like sine of 2x equals a half instead of just sine x. So this is a multiple angle. You would solve it as if it were just sine of y equals 2 1/2, and then we deal with that 2x once we're done with that. And then the property of product of zeros. So if you can factor an equation set equal to 0, then all you have to do is find the 0 of each factor. So let's take a look at some examples here from the practice work. And so here we have a function in quadratic form. So we want to find all of the solutions of this. So first thing we want to do is I want to look at this thing as if, and I have a mistake here that I need to fix real quick here. So I'm gonna, okay, and we're back. I fixed it now. It needs to read 2 sine squared x minus sine x minus 1 equal to 0. So the first thing we want to do is we want to look at this. Oh, don't we want to look at this equation as if it were 2x squared minus x minus 1 equal to 0, and factor that. So we want to factor this expression here. And clearly, if I go 2x plus 1 and then x minus 1, 2x squared, or 2x times x gives me 2x squared. 2x times negative 1 is negative x. 1 times x is 1x plus the negative 2x gives me a negative x, and then 1 times negative 1 gives me the 1 there. And so if I use that instead of just x, I have sine x. We can rewrite this one as 2, oh, that's not a very good 2, let's fix that. 2 sine x plus 1, and then sine x minus 1, set it equal to 0. Now, we only have to find the solutions over 0 to 2 pi, so that makes it a little bit easier. And so basically I'm going to set each of these two equal to 0. So I'm doing a couple different things. I'm factoring, and then I'm going to use the property of the product of zeros here. So I'm going to go 2 sine x plus 1 equal to 0, and then sine x minus 1 equal to 0. And so real quick, sine x equals to negative 1/2, and then sine x equals to 1. All right, so I go back to my unit circle, and again, hopefully you've got this unit circle down. We don't have to worry about it a whole lot, but we need to figure out where what angle measures gives me a sine of negative, gives me a y of negative 1/2. Well, 7 pi over 6 and 11 pi over 6 give me that. So the solutions for this first one, x, oops, I need a pen, x equal to, what did I say, 7 pi over 6 and 11 pi over 6, and then we need a sine of x equal to 1. So what angle measure gives me a y equal to 1? Clearly, that's the only one on the unit circle from 0 to 2 pi, so pi over 2 is the last solution. And that's it for that one. All right, next one, solve over this expression. So I've got secant plus tangent equal to 1. All right, so let's see, what am I going to do here? This one, I'm going to do something a little bit different. I'm going to multiply this thing by secant x minus tangent x, both sides, as secant x plus tangent x equal to 1 times secant x minus tangent x. And so again, so on this side I'm distributing, and remember a plus b times a minus b is equal to a squared minus b squared. So I get secant squared x minus tangent squared x equaling to 1 times, and then 1, oh, we won't write that, we'll just do the multiplication. 1 times anything is just that thing, secant x minus tangent x. And from our trig identity cheat sheet, if I subtract tangent x, or tangent squared x, from both sides, I get 1 equal to secant squared x minus tangent squared x. And so this thing is equal to 1. And these two things are equal to each other. And so since secant plus tangent is equal to 1, and secant minus tangent is also equal to 1, they must be equal to each other. So I can take this expression here and this expression there, actually let's use a different color, and this expression there, and set them equal to each other and say secant x plus tangent x equals secant x minus tangent x. The first equation, or how about this equation? And the first equation are equal to each other. All right, and so let's see here. If I add tangent to both sides and subtract secant from both sides, I will get we're setting this equal to 0. So when I subtract tangent or secant x from both sides, so minus secant x minus secant x, and I get plus tangent x plus tangent x. These two cancel, those two cancel, those cancel, and I get 2 tangent x equal to 0. And so let's see, if I set that equal to, so this means that tangent x equals to 0, has to, and if tangent x equals to 0, we can substitute tangent x equal to 0 into the first equation. And so I get secant x plus 0 equaling to 1, and therefore secant equals to 1. So tangent x equals to 0, and tangent x equals to 1. And let's see here. Tangent x equals to 0 when sine is equal to 0 over those two. And so sine is equal to 0 when x is equal to 0 and pi. And then secant x, remember secant x is 1 over cosine x equal to 1. And so cosine is equal to 1 over 0 to 2 pi at only one place, and that's also at 0. So here's my final answer. That's what I'm going to go with. Next solution, solve the equation. Cosine times cosine x minus 1 equal to 0. Well, I already have a product and they're both equal to 0. So all I have to do is set each factor equal to 0. And so cosine x equals to 0 and cosine x minus 1 equals to 0. And so cosine x equaling to 1, well, cosine x equals to 0 at 2 places on the unit circle. Let's go back up to the unit circle. Cosine is the x value, so it equals at pi over 2 and 3 pi over 2. Oops, didn't quite where I wanted it to be. So pi over 2 and 3 pi over 2, and the cosine of x equals to 1 only once on that interval, and that would be at 0. Okay, there we go. Oops, this is solve the equation. So we have to say this is not just the unit circle. And so since none of these match up, we're just going to write them all in terms of that plus 2 pi. So my final answer is going to be pi over 2 plus 2 pi and, or excuse me, plus 2 pi n, comma 3 pi over 2 plus 2 pi n plus 2 pi n and just 2 pi n, because 0 plus 2 pi n would just be 0, right? Don't need that plus. Where n is an integer. I don't like that. Let's make it look nicer. 3 pi over 2 plus 2 pi n. There we go. Next. Come on, next. Next. Not responding. There we go. Solve over 0 to 2 pi. So we're just solving the first unit circle. And here's an instance where I have sine squared theta and I have cosine x. So here I want to convert sine squared x into terms of cosine x. We can do that because remember the Pythagorean identity, sine squared plus cosine squared equals 1. If we subtract the cosine squared from both sides, we have sine squared x equals 1 minus cosine squared x. So I'll have 2 times 1 minus cosine squared x equals 2 plus cosine x. And I distribute. That'll give me 2 minus 2 cosine squared x equals 2 plus cosine x. And so subtract. And so if I subtract 2's from both sides, that'll cancel. If I and then if I add 2 cosine squared x to both sides, I'll get 2 cosine squared x plus cosine x equals to 0. So subtract 2 and add 2 cosine squared x to both sides. And so here I'm just going to factor. And so if I factor out a cosine, I'll have cosine x is 2 cosine x plus 1 equaling to 0. And so I'm going to set each factor equal to 0. All right, so I got cosine x equals to 0 and 2 cosine x plus 1 equal to 0. Solve individually. So cosine x equals to 0 when x equals to 0. And so cosine x equals to negative 1/2. And so cosine x equals to negative 1/2 when the x values are negative 1/2. So let's see here, 2 pi over 3 and then 4 pi over 3. And that's all of the values over the interval 0 to 2 pi. All right, last one, solve this one. This is a multiple angle formula. So I'm going to say solve this as if it were sine of y equal to negative square root of 3 over 2. So if I say sine y equals negative square root of 3 over 2, that actually becomes fairly easy to solve. I just look for the angles that gives me a y value of negative square root of 3 over 2 on the unit circle. All right, and so those values, the y values, say negative square root of 3 over 2 as a y value is 4 pi over 3 and 5 pi over 3. So if I come down here, I get y equals 4 pi over 3 and 5 pi over 3. Now, if it were just y, that'd be it, because the next one would be all the way around the circle and we'd be outside the interval 0 to 2 pi. But this isn't what we really have. We have actually 2x. So replace y with 2x. Okay, so I've got 2x equals 4 pi over 3 comma 5 pi over 3. All right, so divide both sides by 2, and I get x equals, and I get 4 pi over 3 divided by 2 will be 4 pi over 6, and 5 pi over 3 divided by 2 will be 5 pi over 6. Now, 5 pi over 6, you'll notice on your unit circle, 5 pi over 6 isn't even halfway around. So there's actually the opportunity that there are more solutions when you have this multiple angle formula. So if I think about it, if I take that 4 pi over 3 and I say, okay, what would the next one be? So 4 pi over 3 all the way back around. So 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3. Did I count that right? 5, 6, 7, 8, 9, 10. 10 pi over 3. Yeah, that's going to be right. 10 pi over 3 would be the next value in that sequence. So 10 pi over 3. And then the next one after that, that also works, would be 11 pi over 3. And that makes sense because we're adding that 2 pi again. And 2 pi in thirds would be 6 pi over 3. So if I go 4 pi over 3 plus 6 pi over 3, I get my 10 pi over 3. Now, this is not in this interval, but when I divide by 2, I get 10 pi over 6, and I get 11 pi over 6. And 11 pi over 6 is still, it's a solution, and it's still in that interval 0 to 2 pi. Now, there aren't any more because the next time I go even 1 pi over 6, I'm up to 2 pi. So we're done there. But we should simplify because 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 does not reduce. 10 pi over 6 is 5 pi over 3. And then 11 pi over 6 does not reduce. And that's our final answer. Whew, that's a little bit longer than the last couple, but we are to the end. So the Star Wars fun fact of the day is blue milk appears in Episode 2, Episode 4, and in Rogue One. It must be quite delicious and also very nutritious. Have a good day, folks. I'll see you in class. Goodbye.